Hello and welcome along to this Bentley Success Factors webinar on deterministic stability in MAXSURF. My name is James Clarkson and I'm a naval architect and one of the technical support engineers working with MAXSURF. When we first look at stability compliance for design, we always think it's going to be easy. It's a few rules about GM0, GZ and a healing lever. Invariably, it then starts to get a bit more complex than we thought. MAXSURF has some fantastic tools for assessing compliance of your vessel. MAXSURF can do the maths for you, but like any software, you still need to know what you want. So today's webinar is looking at how we set up the model for various deterministic assessments. The topics we cover look at translating the words and regulations into the numbers that make you pass or fail. We cover interpretation of the predefined rules and how you go about creating your own. We also look at some of the calculations that add complexity to your model, healing arm calculations, windage, partial flooding, and working with limiting VCG. The final part today is worth hanging around for. It's very frustrating when something is wrong and you can't tell what. We're going to discuss some of the problems that frequently come up and how not to get caught out. Nearly all of the stability criteria can be divided into three main groups. We have GM0, our initial stability. We also have the GZ curve and various points along that GZ curve, such as intersections with the healing levers and the maximum GZ as marked. We also have the area under the GZ curve, such as the area up to a maximum GZ, and we have comparisons of that area to a negative rollback area. There are a handful of other measures, such as freeboard at various conditions, that we won't go into. The tricky part is converting the text written in the regulations into the correct input for MAXSURF. Each regulation uses a different combination of lower bounds, upper bounds, nomenclature, etc. to define the areas and points in this graph. As an example, IMO measures the area under the graph up to the lesser of 30 degrees, or the angle of vanishing stability, or the point of down flooding. Interpreting this data into MAXSURF is a bit tricky, and you need to understand how MAXSURF is defining and using each of those points. A good place to start is looking at these rules. I have open here the sample workboat file. It's part of these sample files that ship with the software. I'm going to open up the rule sets in here. Let's take a minute to have a look at the anatomy of this criteria window. I'm just going to pull up one of these criteria. So the first part we'll look at is the criteria list on the left-hand side. So these are all of the different criteria that are installed in the software for you to apply to your stability analysis. Each of these criteria has a calculation behind it. The inputs for those criteria are shown in this criteria details window. We can select what values are inputs for our criteria, and we can select which of these points or different limitations are applied to our criteria. Often these calculations get a little bit complex, so thankfully there's a help section here as well. These ones will either reference the source for the criteria or we'll discuss the inputs and how the calculation is done. Now, sometimes our criteria are applicable to an intact case, sometimes to a damaged case. So down here, we're allowed to select if we test this criterion only on the intact or possibly on the damage as well. And this final box here is water on deck. Once we're done in our criteria window, we can close this. We have two choices. We can either recalculate the criteria against the results we have, or we can just close the window straight away without recalculating. In this criteria window, you'll see that we have around 20 or so different regulators criteria pre-installed. And within these, there's around about 1,000 different rules that you can apply to your vessel. So in a lot of cases, we've done the hard work for you. All you need to do is confirm what is there and confirm that it's applicable to your design. So this is the easiest scenario. In scenario 2, we find that our regulator is not on the list of rules. In this case, we need to create that set of rules ourselves. Often, state regulators have mirrored other regulations. So the rules that apply for your country may be just the same as the IMO regulations, it may be these exact same regulations, but they've just been repeated for your state regulator. Often it's worthwhile doing an internet search on a phrase from your regulations to see if that phrase is common with other regulations. In this case, all you need to do is copy and paste that criteria and rename it to a suitable name for you. Scenario 3 is when we have to start at the beginning to develop our own rule set. If you do need to make up your own rules, this is how we go about it. There are 3 different groups at the top here in bold. There's criteria, healing arms, and calculations. The calculations are for when the rule specifies something that's too complicated to calculate in the rule itself. So we cross-reference to an external calculation. In this case, we have a rule that looks up the length, displacement, and other particulars of the vessel to create a value that is used as a required minimum GM. These healing levers are similar, that you may use it because it's a complicated calculation or because it's the one healing lever that's referenced by more than one rule. You'll see that we have healing arms for some generic cases, wind healing and passenger that are quite frequently used, and some more specific healing arms like lifting and towing. So these calculations and healing arms are then cross-referenced into these parent criteria. And here are the bases for all of the calculations that we have in this 1000 predefined criteria. So all of these have been calculated from the correct one of these. It can be tricky to find out which one has the correct inputs and outputs that you're after. So we do have some nice help written out for these criteria. Often they'll also include diagrams, etc. So now I'll walk you through the steps to create some rules based on these parent criteria. So what we're going to do now is create a custom set of rules by selecting a variety of these different criteria that demonstrate how to do the cross-referencing into healing arms and the cross-references into calculations. The first step we have to do is to add a new group in. So I'm going to call that group Custom Regulations. And then we can start finding the criteria that we want to bring across. The first one I'm going to grab is this value of GMT. Now you'll see that this one can cross-reference a calculation from the list. In the description for this rule, we can see that it's looking for a minimum value of GM at a given heel angle. Now we're going to use this calculation from the list from a cross-reference, and the first thing we've got to do is go and copy a calculation down. So I'm taking this required GM, copying, pasting into our custom regulations. These need to sit in the same folder to be able to cross-reference them. So now when I go into my value of GM, select on this drop-down menu, I can see here's the cross-reference to the rule that I've specified. So that cross-reference is now done. The only choice we have in this rule is do we want to take the angle at a specified angle of heel or the angle of equilibrium? So I'm going to take the angle of equilibrium, which should be upright for our vessel. When we come into this rule, we can take a look at these numbers and we can adapt that lever magnitude, and we can also select which of these angles we want to be able to apply. So that's our first rule and the first cross-reference, a calculation for a rule. The next rule we're going to apply is a healing arm rule. So you'll see there are two sets of healing arm rules here. There are standalone criteria and cross-reference criteria. Now the standalone criteria include all of the values within the rule calculation. The cross-referenced ones will allow us to select a healing arm from the list and specify something about it. Now we're going to take a simple rule here. We're going to look at the value of the GZ at equilibrium. So once again, I copy and paste that down into my custom regulations to work with it. Rename it. And you'll see that here we're being asked to select a healing arm from the list. At the moment, we haven't specified one, so we need to go and find one. And I'm just going to take this standard wind healing arm. Now we can see in this wind healing arm that we get to specify area in different ways and where that area is acting on, the lever arm that's acting on. And we're going to come back and talk about those later. We can then come back into our rule and add the cross-reference through to that. One of the advantages of using that cross-reference is that if we have multiple rules that use healing arms, then we only need to find that healing arm once, and we can have multiple rules cross-referenced to a single healing arm. We now have this option to use the steady wind healing or the gust. I'm going to leave it at steady. Now I will put in a reminder here that if you have a wind healing arm, but you don't have a rule that cross-references it, then it won't be included in the calculation. You'll have it selected, you'll run the calculation, it won't show up on your graph, and when you come back in, it will have been deselected. So if the lever isn't being utilized, then it's disregarded in the calculation. The final criteria we're going to add today is we're going to go looking for a tricky one. So we're going to have an area under the GZ curve. You can see in this rule there's quite a few different input variables that we can work with. This description essentially says that the required area under the GZ curve changes depending on the angle at which a certain integration limit occurs. So that can be any of these things specified in the list, such as angle of vanishing stability, angle of flooding, maximum GZ, etc. So let's copy that rule across. Now, unlike the rules that we've dealt with previously, this rule doesn't have any cross-references, so everything that we need for this rule is included here already. I'm just going to deselect some of these that I don't believe will apply to us. And now that we have all of our regulations defined, final step is that we go and select them, quick check that we haven't got other ones selected, and we can close that dialog. So now when we go and run large angle stability, we have predefined loading cases and we're looking at intact right now. This model will run through, and as it runs through, you can see that we're putting together that GZ curve. Now, the first thing we can observe here is that we have 0 wind healing arm. So we can go back in and we can check our criteria. And sure enough, we have specified a total area here. From the graph, we can now see that this information looks right. And if we come across to our rules, then we can see that we have passes all down this column. And the calculations of numbers that are led in to each of those calculations. This data is currently shown in verbose mode. If we want to simplify this data output, then we can through display and data format, and we can choose to have this results table in compact format. And you'll see that there's also an option here to have the results in the report either in verbose or compact format. I'm going to leave it in verbose for now because we're talking about some of the calculations that go into this output. Now, the next bit I want to talk about is to look further into this wind healing arm. There are 3 different methods for calculating windage area within MAXSURF, and they range in complexity from doing nothing through to specifying each surface that contributes to that windage area. So the first approach of do nothing is to do nothing. If you do absolutely nothing, then MAXSURF will calculate this area above the waterline and calculate this area below the waterline, and we'll use those 2 centroids to calculate the healing arm based on that, the size and and magnitude of the arms. So that's if you do absolutely nothing. However, say often we have a deck house, or perhaps in this load case, we have some deck cargo. And so these are things that we don't necessarily need to include in our model, but they will contribute to the windage in the stability model. So when we have these things, what we can do is to specify an additional area, and that's done in that criteria window. So you'll see here, and we have it checked already, we have option to specify an additional area, and I've already specified 10 square meters in there. So MAXSURF will calculate the area of the hull, and then we tell it that we have an additional 10 square meters. We have two separate options for calculating the height of that area, and we can give it some different options for calculating the centroid of that underwater area that forms the opposite end of the lever arm, the healing lever arm. The next option we have is, instead of specifying an additional area, we specify a total area. You might want to specify a total area is that the number calculated by MAXSURF isn't actually correct. When MAXSURF calculates the area of a vessel, if we had, say, a large overhanging superstructure on here, MAXSURF would calculate this area by linking up the highest point and the lowest point in the section lines. So as you can see in this situation, there's a large area through here that isn't actually windage area, but would get included in MAXSURF's area calculation. So you can override the calculation that MAXSURF has done by specifying a total area. Now, the final option we have for specifying the windage area is to do an accurate calculation on all of the windage surfaces through the data menu and windage area groups. In here, we can specify two groups. We can specify all of the underwater surfaces and all of the windage above water surfaces. So I'm going to start with the windage area. These are the port and starboard sides of all my surfaces. Now for this vessel, I'm just going to select on the starboard side surfaces, and in actual fact, I don't need those. This is the bow thruster surfaces, and they're always below waterline. So I'm only going to look at one half the surfaces. The more surfaces you select in that list, the slower the calculation will run. Now for underwater, I will select all of these. There is a portion of the top sides that goes underwater. So all of these surfaces have some underwater area. Now MAXSURF is clever enough to remove any above water areas from the underwater calc, and vice versa for the windage area. We can specify drag coefficients, shielding coefficients, and another user-defined coefficient. So if we had, say, a shielded part of the vessel, then we can create another windage group and give that group of surfaces a different factor. Likewise, if we had, say, a semi-submersible that's supported on columns, we can have a different drag factor for those columns than we have for the rest of the group. So now when I say OK to that, it displays the windage surfaces, or I can turn that on and off through windage profile. And we can see the above and below water areas. Now the final step of windage area to talk about is the inclined windage profile. As your vessel rolls, the area of the hull exposed to the wind changes. In most ship-shaped vessels, that change is insignificant, and we're allowed to use our upright windage area in those calculations. However, in some vessels, we want to recalculate that area as we incline the vessel. Such vessels would be a semi-submersible or something covered under the MODU code, where the upright windage area is quite low, but as the vessel heels and that deck is exposed to the wind, the windage area increases significantly. Under the preference menu is where you'll find the option to calculate the inclined wind profile. So you can select it on or off as need be. As a general rule of thumb, you won't use it because it does add significant amount of time to your calculation. At every step of the way for your large angle stability, you need to go through and recalculate your area, and that will add a significant amount of time to your calculation. Now, the next item we're going to talk about are damage cases. Most of us are familiar with the concept of damage. So today we're going to talk about intermediate damage or partial flooding. If we look here under the HSC code, then there are two rules here that apply to intermediate stages of flooding. So these aren't asking if you're stable in your intact case or stable in your damaged case. They're asking if you're stable on your way to being damaged. In these cases, we specify a percentage filling in the tanks that represents how flooded that tank is at that point in time. So let me pull up a damaged tank. So this is a standard damage scenario. MAXSURF uses a lost buoyancy method when dealing with damaged tanks. There is an alternative system that is not implemented in MAXSURF, that is the added weight method. In a lost buoyancy method, we remove a section of buoyancy from the hull that was occupied by the tank that has been damaged. The weight of the steel in the ship is still exactly the same, but the buoyancy provided by that ship has been reduced by the damage. In an added weight scenario, fluid flows into the hull, increases the displacement of the ship. In both scenarios, the ship will sink by the same amount. The finished outcome is the same, and if you account for the free surface moments, both methods will give the exact same righting moment. The difference between the two methods is if you then divide that righting moment by the displacement to get the GZ, then the added weight method with a larger displacement will give you a lower GZ than the lost buoyancy method. And before we run that, I'm just going to check on a few things. Now, to improve the accuracy, I'm going to simulate fluid movements in the tanks. We're also going to ensure that we have enabled empty damage tanks. This is something you might want to consider or not. If you have cargo in a tank that's damaged, do you want that cargo to flow out and be replaced by seawater, or do you want it to remain in that same condition? The next one is to enable the partial flooding. We need to select this option at the bottom, enable partial flooding. So having done that, I can come into my damage case window, and Control A adds a new damage case. So here you can see we have two options. We have partially flooded rooms that share a common waterline, or ones that have individual waterlines. So we'll start with a common waterline. Now I'm going to duplicate the damage from the SB aft case. To specify the partial flooding, we just type in a percentage fill for each of the damaged tanks. Now what you'll notice here is that we've specified a common filling level. And so if I change the filling in one of these partially flooded tanks, then it changes it for all of them. If one of these tanks was fully flooded, then it stays fully flooded. So that's the common waterline. And now the next one we're going to add in, this time I'll go through the menu, add a damage case, is an individual case where we have individual waterlines. So this time we're going to give a random assortment of filling levels. For these filling levels, we're never going to flood a tank higher than the current waterline. So when we say 80% filled, it will be to the current waterline or 80%, but not higher. So the first case I'm going to run is the fully flooded case, just so we can see what that one looks like. So we can see we've got quite a trim by the stern. This tank here is clearly flooded to its full amount. These tanks are flooded up to the waterline. Now if I come and have a look in my results window, then we can see here that we have that diesel tank is 100% flooded. These two are flooded up to the waterline, so they're labelled at 93 and 63% of capacity. So this time, let's go and have a look at when we fill to a common waterline. So we've specified 10%. So 10% flooded isn't particularly far away from that intact case. So now you can see there is one consistent parallel line that covers all of these tanks. If we go back and look in that room definition, then you'll see that there's a variety of filling levels in here. There are two that are filled to 100%, and these higher up tanks are only filled to 2%. If you were to do a sum total on their full volumes and those percentages, then you'll come out a number of 10% filling across all of those tanks. The scenario with the individual water lines represents a case where you've got progressive flooding, so you've perhaps got a hole into one compartment that's slowly filling into the next compartment or something. When we run this situation, we can see that there are different flooding levels in these different tanks. We turn on these tank edges for a second so we can see where they are. So we can see the different tank levels. There is a heel in this damaged condition, which is why we're seeing these two different deck edges in the profile view. Looking at the room definition window, and we can see that some of these have been flooded to their maximum prescribed filling level, and some of these compartments have been flooded. Sorry, this one will be within tolerance of 40% filling, and this compartment has been filled up to the waterline and not higher than the waterline. So there you have the partial flooding, which is required by some of the rule sets and specifies that intermediate situation between intact and damage while the ship is still flooding. So the next thing we're going to talk about is to go back to the intact case, and we're going to talk about a limiting kg analysis. The limiting kg analysis runs a series of large angle stability analyses, iterating to find the load case with the highest permissible VCG that passes all of the criteria. I really like a limiting kg analysis for early design, where you can define an immovable limit on how high that center of gravity can go without changes to the hull shape, or if you're limited by a damage case, without changes to your internal configuration. You cannot get the VCG higher than what you find in the limiting VCG case. So it draws a very firm line in the sand that you can use with the other engineers as it do not exceed weight and height. To run the analysis, we need to specify that we're in limiting kg. For an intact case, it's not dependent on load case. And then we specify heel setup. So I've got it from -120 to 180 in steps of 10 degrees. Now remember that because we are iterating, that we are doing a lot of calculations here, so it can take some time. Trim, I want the vessel to have a 0 trim in its upright condition. So MAXSURF will determine a load case where the LCG is at 0, and we'll work from that. Then we're going to run this analysis over a series of displacements. So I have it running from 60 tons up to 80 tons in increments of 5 tons. 5 different weights that I'll do on the way through. So when I run this analysis, we can see the vessel going through a series of tests. And we can see the program starting to iterate on how high we can get this VCG before it fails. We also get told which criteria was the one that caused it to fail. The program keeps iterating to get a result within the tolerance specified in your preferences. We're also developing a graph here showing those results. I'm going to skip ahead a little bit because this analysis does take a little while and takes longer depending on how much detail you want in it. Now the analysis is complete, we can see that depending on what displacement we're on, a different rule has caused the limit to that VCG, and that's caused us to have quite a bit of change of shape in our limiting graph. And we can also see that the highest permissible VCG doesn't occur at the lightest displacement or the heaviest displacement, but occurs somewhere in the middle. Now we can cross-check the results from our limiting KG by creating a load case that mirrors one of these situations. So I'm going to take this 75-ton case and recreate the data in a new load case. And we'll also check on our heel is set up the same and that our trim is set up the same. So free trim to load case. When we run that, what we should find is that we get a GZ curve and that each of these GZ criteria pass. If I was to tweak this up by just a few millimeters and run that again, then as expected, we can see the criteria starting to fail. So that limiting VCG is really good for having a defined limit where we know we can't go beyond that, and we'll need a geometry change to be able to go any further. Now that wraps up the technical side of today's presentation, but I did promise you that we would have one final discussion about a couple of troubleshooting issues that often come up in MAXSURF. Now the first troubleshooting thing we're going to talk about is sections forming. You can see this model that I've knocked together that looks suspiciously like I've shrunken two workboats and put them next to each other with a deck in between. And you'll see that I've intentionally not trimmed these surfaces between the deck and the side of the hull. Now when MAXSURF forms sections, it needs to be able to create one line that runs from one hull across the other side and back again. MAXSURF can close one gap, but can't close more than one gap. With this untrimmed surface, MAXSURF will get to this point, and there are three directions it could be trying to form a section line in. MAXSURF doesn't know the correct way to go and is likely to incorrectly form that section. Now that section represents an area and a centroid that gets taken to a volume that is then used for the volume calculations for the boat. So let me turn on the sections here and we'll see what's happened. So here you can see that the sections in the bow look okay, but as we get into this section where the deck is, we get a section forming across, and then it sees this edge up here and it comes back in. The clearest place to go and look at these section lines is in the body plan view with the show single hull section in body plan selected. Then we can click up here and use the arrow keys to cycle through. And you can see that that shape isn't correct. Through the bow it is correct, and further aft it isn't. So the error that we have here is that we don't have a continuous shape. This has come down to a trimming issue. If we took this back into Modeler and fixed up that trimming, then we'd likely see that, that it forms correctly. Often with catamarans, it's a good idea to put a deck on. There is one little behind the scenes shortcut that I can show you. With this recalculate hull sections, if you do have maybe just one hull section that isn't formed properly, if you click Shift while selecting on that, we do get the opportunity to deselect a given station if we just have maybe 1 or 2 stations that aren't forming correctly, we can deselect one station, remove it from use, and remove that error. To show an example of how this is going wrong, if I was to run just an equilibrium analysis on this vessel, we'd expect it to sit at an even keel, but because there are no sections defining this corner at all, there is no buoyancy there and it's nearly entirely submerged. Now the other one that often comes up is you come across an issue where the vessel isn't reporting any trim. It may be sitting entirely bowed down, but there is no trim being reported by MAXSURF. And that comes down to the frame of reference. The frame of reference needs to be set in modular before you bring into stability. And if you have the aft perpendicular and forward perpendicular both sitting on top of each other at midships, then there is no trim. There is no difference in height between the forward perpendicular and aft perpendicular, and MAXSURF won't be able to report any trim, and you won't get the right results. That brings us to the end of today's presentation. I'd like to thank you all very much for coming along. My name is James Clarkson, and it's been my pleasure to present this to you.